So technically, we have two different types of beams, that is laterally supported beams and the laterally unsupported beams. So this is in particular with the steel structures. Okay. Whereas in concrete structures, you must have seen the different types of beams, that is a single reinforced beam, double reinforced beam, and all, right? So based on the neutral axis depth values, again, you have the three different types of sections: under reinforced section, over reinforced section, balance section. So here also you will find more or less similar to the concrete beams, but in steel structures, the beams are broadly classified into two types. One is laterally supported beams, and the second one is laterally unsupported beams. Remember, laterally supported beams are also called as laterally restrained beams. Okay, please make sure that laterally supported beams are also called as laterally restrained beams. You can make it here, that is laterally restrained beams, which are also called as laterally supported beams, and laterally unrestrained beams are called as laterally unsupported beams. These are the other names of these beams. So laterally supported beams are also called as laterally restrained beams, and laterally unsupported beams are called as laterally unrestrained beams. Now let's talk about what is this laterally supported beam and unsupported beam. So coming to the understanding of laterally supported beam, all you have to do is consider an I section, or you can consider any section, but generally if you are designing beams, it is mandatory to design an I section instead of the channel section or angle section, because the channel section and angle sections are not sufficient enough to design a beam or to consider as a beam. So if you're designing a beam member, it must be an I section. 99.9%, it must be an I section only. Again, in I section, you have different types: ISLB, ISJB, and all. Okay, I'll talk about that a little later. So consider an I section. Okay. So let's consider an I section. And to this I section, you know that you have the axis, which is exactly dividing the member into two equal parts, both along the ZZ axis as well as along YY axis. Okay, it is a member which is equally dividing the section into two equal halves, both along the Z axis as well as along the Y axis. Now here, due to the application of the load on the beam, okay, due to the application of load on the beam will get bent. That is very common. Suppose you have a beam in this way, I'm just considering in this direction. So you have a beam in this way, and as soon as I apply the load on the beam, it need not be a concentrated load, it can be an UDL also. As soon as I apply the load on the beam, due to the application of the load, the beam will start to bend. Okay, even though the bending is very minimum, but however, the beam will start to bend. Now, your subject, okay, what is your motive is you need to restrict this bending, right? That is our key focus, because if you are applying certain amount of load on a beam, if the beam member is getting bent, that means your structure is not safe, that the member which you have designed is not safe. So ultimately what you're going to do is you're going to make sure the stability of the structure without any bending or without any deformation. Now here what happens is, if the beam is subjected to only bending, that means as soon as you apply the load, if you are finding only bending in the beam, such kind of beams are called as laterally supported beams or laterally restrained beams. Remember, if you are applying load on a beam member, it will be a steel beam, not the concrete beam. Okay, so if you are applying certain amount of load on a steel beam, as soon as you try to apply certain amount of load on a steel beam, what happens is, if the beam is subjected only to bending, then it is called as a laterally supported beam. So in laterally supported beam, you will be focusing only on the beam which has only the bending. Okay, remember here the beam will have only the bending. But what is laterally unsupported beam? So in laterally unsupported beam, okay, you will have the bending pattern. Okay, you will have the bending as well as the twisting will also be there in the member. Okay, so in laterally unsupported beam, you will have the bending as well as twisting to the member. Now, how does this twisting moment comes here? It is because suppose you are having a same member and I am applying the load. Suppose, say, for example, I'm applying 100 kilonewtons of load. Due to this 100 kilonewtons of load, it is very sure that certain amount of bending pattern will be observed. Now, if the end conditions of the beam, suppose, say, for example, if the end conditions are just the hinge supports, it won't be that way. But if the end supports are hinge support, then you might also expect certain kind of moment in the member, right? It can be a positive moment or negative moment. So when there is an application of a load on a steel beam, if you experience only bending, okay, if you experience only bending, then it is called as a laterally supported beam. Along with bending, if you are also experiencing certain kind of moment, then it is called as a laterally unsupported beams. There is a simple difference between laterally supported beams and unsupported beams. So in laterally supported beams, the bending is accompanied, whereas in laterally unsupported beams, along with bending, you will also experience certain kind of moment, and hence it is called as a laterally unsupported beam. Now, if you compare between the laterally supported beam and the laterally unsupported beam, which one will be more severe? That is our question. Which one will cause more failure, or which one will be dangerous to design? So it is always very sure that in laterally supported beams, you have only bending. That means the failure of the laterally supported beams will be very less because you are accompanied with only bending. But whereas in laterally unsupported beams, you have the bending as well as the twisting. That means two different kinds of forces are acting on the laterally unsupported beam. So from this, it is very sure that laterally unsupported beams are the beams which are subjected to heavy amounts of failure. Okay. So that's what happens. So laterally unsupported beam, since it is subjected to bending and twisting, there won't be any lateral support on the beam to resist failure. So instead, it fails. Okay? So since in laterally unsupported beams, you don't have any support to the member. Okay. So since there are no support to the members, what happens is it is quite sure that laterally unsupported beams will get failed initially when you compare with laterally supported beams. And here you can also define the laterally supported and unsupported beams in a different way. I'll show you that what is the difference. So here you can see a beam which does not laterally move nor rotate. That is what exactly it says. It says you have only the bending in the member. So a beam which does not laterally move, a laterally supported beam will not move at all. And it doesn't have any kind of rotation also. It will have only the deflection or the due to this bending, okay, which does not laterally move nor rotate, it is called as a laterally supported beam. Now to consider this one, it depends on the kind of restraint provided at the supports. That is what I have told. So if you have the fixed supports at the ends, you might not see the bending very accurately. If you have the hinge supports, you can experience the bending, or you can visually see the bending of the member. And that is the reason why it is clearly said that it depends upon the kind of restraint. That means it depends on the type of the support which is available at both the ends of the beam. So for example, if you want to consider a beam is supporting a slab, we all know that beams support slab. And this beam will be laterally supported beam. It is because you have certain kind of support. A slab will act as a support to the beam. Okay, you have a beam, consider this as a slab, and you have a beam here. Okay, what does slab act is? Slab act as the support member to the beam. So, and hence it is called as the laterally supported beams. So whatever the beams that are there near to the slabs, those are called as laterally supported beams because all these beams are supported by slabs. Now, so here you can see the clear-cut difference between the laterally unsupported beams and laterally supported beams. So in the second figure, consider this as a second figure and this as the first figure. Let's look at the second figure initially. See here you have the 4 different eye sections. So this is one of the eye section, and this is the second eye section, third and fourth eye section. Now in all these eye sections, consider that you don't have these supports. Okay, whatever the thick black colored things which you are seeing, you assume that you don't have these supports in the initially. Okay, Now what happens is, if you are applying certain amount of load from this direction, that is, you are trying to apply the load on the web of the section. You're trying to apply the load on the web of the section. Due to the application of load on the web of the I section, what happens is the member I section will tend to bend in this way. Okay, probably in this way, due to the lateral load which is coming onto the member. Now, your motive is to ensure that the member which has got bent to be in the stable position. That means it should be in the perfect I or perfect I shape. Now, what will you do? The only thing which you can do is to provide supports. Okay, the thick colored things which you are seeing, to provide supports in order to resist the bending of the member. And hence those are called as laterally supported beams. So if you are providing support in between the two sections, then those are called as laterally supported beams. Now here, if you observe the second beam and the third beam, that is the second I section and third I section, here you can see very clearly that you don't have any lateral supports in the middle portions. You have the lateral supports only at the ends, right? You can see the lateral support here, and you can also see the lateral support here, right? So this beam, that is the second and third beam, you can say it as, there is a maximum amount of deflection will be there, that is the bending will be there, and also maximum amount of deformation will also be there. So here you can say that there is higher chance of failure of second and third beams will be more when you compare with the first and the fourth beams. It is because the first and fourth beams are laterally supported. It is said that they have proper supports. The first and the fourth beam have proper supports. Even the second and third beam are also having supports, but they are having supports at the edges of the member. They don't have supports at the intermediate portions, right? So when they don't have supports at the intermediate portions, it is very clear that you might experience the bending in the member, and also this bending will be accompanied by certain kind of twisting. So this is what the laterally supported beams are. So sometimes the laterally supported beams can be provided the supports in this way, and they can also be provided in this way, as you see in the second figure. So they are nothing but the lacing system which we have studied in the compression members, and they can be provided in the form of battening system. So even in the design of beams also, you can provide the lacing system as well as the battening systems. So this is all about the laterally supported beams. So in laterally supported beams, only bending phenomena will be there. And to avoid this bending, what you're going to provide is, you're going to provide the lateral supports to the sections. So when you provide lateral supports to the section, you don't find any amount of bending in the member. So when you don't find any amount of bending in the member, it is said as a safe member, or it is considered as a safe beam. So always remember, you're going to provide the supports at the both at the edges of the section as well as at the intermediate portions of the section. That is what we have done here in this figure. Okay, in the first and the third, in the first and the last parts of the section. So this is all about the laterally supported beams. Whereas in the laterally unsupported beams, you don't have any kinds of supports in the member. So the only beams will be there, or just the I sections will be there in this way. You have one I section and you have the second I section. You don't find any kinds of supports in between the two I sections. So those are called as laterally unsupported beams. So in laterally unsupported beams, you have the bending phenomena, as well as you also have the second phenomena, which is also very crucial, okay, which is the twisting phenomena, that is the moment phenomena. So these are the two things which will be happening in the laterally unsupported beams. This figure talks about a beam which is provided with a lateral support. So this is the entire portion of the beam. Okay, this entire portion of the beam, and this beam is provided with the lateral supports. A certain kind of flats are provided, Indian standard flats. So what does these flats do is, these flats will act as a resistant towards the failure or towards the bending of the member. Okay, so if you provide certain kind of lateral supports can be in the form of flats or can be in the form of angular sections, can be in the form of channel sections. But most of the times we provide lateral supports in the form of flats. Okay, so by the provision of the lateral support, what happens to the beam is you don't find any kind of deflection or twisting in the member. So this is one of the real-time examples of provision of the lateral supports. There is also one more figure which talks about the laterally supported beams. I'll talk about that figure a little later after discussing of the design procedure. Now let's look at the design procedure of laterally supported beams. So this is available in clause 8.2.1 of IS 800-2007. Okay, so from this clause, you are going to determine the design the laterally supported beam procedure. And before discussing this one, you need to understand one factor which is called as ZPZ. Okay, you need to remember this one, which is plastic section modulus. Remember, ZPZ is nothing but plastic section modulus. And you also have another term which is called as ZEZ, which is elastic section modulus. Elastic section modulus. And remember, as I was telling in the beginning of the class, you have two different types of analysis of the beams. One is the plastic analysis and the second one is the elastic analysis of the beams. But for time being, you just remember what is ZPZ and ZEZ. So the design procedure of laterally supported beams consists of 7 to 8 steps. So in the first step, what you're going to determine is you're going to find out from the given data, you're going to find out the values of the factored bending moment and the factored shear force. So the factored bending moment you can denote with capital M and the factored shear force you can denote with capital V. And again, this determination of bending moment and shear force depends on the type of the support. Okay. For simply supported beam carrying UDL load, you have the factored bending moment as WL square by 8. And for simply supported beam carrying UDL load, the factored shear force is WL by 2. So it changes if it is a simply supported beam with point load, or if it is a cantilever beam with UDL, if it is a cantilever beam with point load at the edge, at the free end, it changes. However, so the first thing which you have to determine from the given data is to find out the factored bending moment and the factored shear force. And from this, a trial section is selected. Okay, in the next step, a trial section is selected based on the plastic section modulus. Remember, a trial section is selected based on ZPZ value. So if you remember the design of compression members as well as the design of tension members, how we have selected the section is based on the area, right? We have found out this one, area required, right? From, if it is a compression member, we have found out PD equals to AE into FCD. We have assumed certain value of FCD and the value of PD will be given in the question. And from this, you're going to get the area required value. And suppose, say, for example, you have got 1000 mm square as the area required value. You're going to choose a specific section. Okay, it depends on the section which is given in the question. From that, you are going to identify the section, right? But here you are not going to do this calculation. That is, area required calculation is not required here. Instead, what you're going to do is you're going to find out the value of ZPZ, which is plastic section modulus. And by using this ZPZ value, you're going to find out, or you're going to select a trial section. Now, how do you calculate this ZPZ value? So ZPZ value is calculated based on this formula. That is M into gamma M naught by Fi. Okay, M into gamma M naught by Fi. From this, you're going to find out the ZPZ, the required value. What is M? It is the factored bending moment. Remember, M represents, capital M represents factored bending moment and capital V represents factored shear force. So, and here the gamma M naught value is taken as 1.1 and Fi value is 250. And you don't have the ZPZ values in the steel tables book. Okay, you cannot get these values from the steel tables book. If you refer Annexer H of IS 800-2007, okay, so refer Annexer H of IS 800-2007. You will find it at the extreme last of the IS 800-2007. So you will have the values of ZPZ for each and every section. Okay, I'll show that once when you are solving the problem. But remember, the values of ZPZ are available in Annexer H of IS 800 2007. Suppose, say for example, you have got the ZPZ required value as 500. Right? Let's just consider this value. So you are going to select a section which has a ZPZ value greater than or equals to 500. So it is always better to go for greater than 500. Okay. Similarly, the area calculation, what we have done in the tension members. Anyways, so this is how you're going to select the trial section. Now, as I said earlier, for the beams, if you are designing the beams, it must be an I beam only. That is what I have said. So you always try to go for the selection of I sections only. Don't go for the selection of channel sections or angle sections. They are proved that the angle sections and the channel sections are unsafe to make the member as a beam. So if you are designing a beam, make sure it must be an I section only. Now in I section, you have different types, that is ISLB, ISJB, ISWB, ISMB, and ISHB. So among all the different types of the I sections, it is said that ISLB, ISMB, and ISWB are the most preferred beam sections, especially the laterally supported beams. So this is available from the literature. If you go through the textbooks, so it is said that you try to prefer ISLB, ISMB, or ISWB based on the ZPZ value. So don't go for the selection of ISHB or the other things. Okay. So if you're selecting or if you're designing the laterally supported beams, make sure of selecting any one of these three sections. But again, in these three sections, don't go for the selection of ISLB, which is a lightweight beam. You can go for either ISMB, which is Indian Standard Medium Weight Beam, or ISWB, which is Indian Standard Wide Flange Beam. So most of the times, or most of the authors will be preferring to go for the selection of ISWB, and it is also okay to go for the selection of ISMB. It's up to our convenience of the selection of the section. But what I personally suggest is don't go for the selection of ISLB, because we generally don't design beams with ISLB. That is lightweight beams we don't design until or unless you are experiencing very less amount of loads on the structure. If you are finding very less amount of loads, then you can go for ISLB. But most of the times you go for the selection of ISMB or ISWB. So that is how the section is selected based on the ZPZ value. So this is the second step. And the third step is the section has to be classified, right? So you know the three different types of section classifications: class 1, class 2, and class 3, right? Plastic, compact, and semi-compact sections, right? So based on B by TF and D by TW, we have seen this one in the design of compression members, right? The same section classification has to be done. That is the class 1 section, class 2 section, and the last one is the class 3 section, right? Plastic section, which is class 1, compact section, which is class 2, and the semi-compact section, which is class 3. So based on this, you are going to classify the section. And the next step, the trial section is checked for shear. Okay, whatever the section which you have considered here, suppose, say for example, by using the ZPZ value, you have obtained ISWB 300. Let's just consider this value. You have selected ISWB 300, and this section has to be checked for shear in the fourth step. How do you check that? So it can be checked in this way, that is the design shear force V. Okay, this one. So the V which we have calculated in the first step, that is the factored shear force. Okay, so the design shear force V is also called as the factored shear force. So the design shear force V shall be less than the design shear capacity, which is VD. Okay, what is it saying? So whatever the shear force value, that is the factored shear force value, should be less than the value of VD. Now, how will you calculate VD value is you have this formula, that is VD equals to Fi by root 3 into gamma m naught into H into T, where Fi value is 250, which is the yield stress, and gamma m naught, you can take it as 1.1, and H is the height of the section. And here T is the thickness of the web. You can make it as TW if you want. Okay, so by using this formula, you are going to find out the value of design shear capacity. And remember, here it should be the value of V must be less than VD. Okay, that is the design shear force V or the factored shear force V should be less than the design shear capacity, which is VD. So this is the fifth step. And here you have to check, that means the beam has to be checked for high shear case or low shear case. So any beam will have two types of shears. One is the high amounts of shear force and second one is low amounts of shear force. Now, how do you identify any beam as a high shear beam or any beam as a low shear beam? You have the conditions for this. Yes. Now the question is, how do you check the beam as a high shear beam or a low shear beam? You have the conditions for this. You have two conditions for this. One is one of the conditions is if the value of V, that is the factored shear force which you have calculated in the first step, is less than or equals to 0.6 VD. So VD value you have calculated in the fifth step. So if the value of V is less than or equals to 0.6 VD, it is considered as a low shear case. Okay. If the value of V is greater than 0.6 VD, it is considered as a high shear case. Okay. So from this, the problem will get divided into two parts. So you have to check for the V and VD values and identify whether V is less than or equals to 0.6 VD or V is greater than 0.6 VD. So if V is less than or equals to 0.6 VD, it is considered as a low shear force or low shear case. For low shear case, you have the separate design procedure. And for if V is greater than 0.6 VD, that is considered as a high shear case. And for high shear case, you have the separate design procedure. So based on the low shear and the high shear case, the problem has to be designed now. Okay. Now let's look at how to design the laterally supported beam if it is a low shear case. So that is our first case, which is the design of the laterally supported beam for low shear case. So this is available in clause 8.2.1.2 of IS 800-2007. You can refer this clause. What does this clause says is MD, okay, that is the design bending strength must be greater than the design moment. How do you calculate this? So the MD value is calculated as beta B into ZP into Fy by gamma m naught. Remember, beta B into ZP into Fy by gamma m naught. Now here, this condition, that is beta B into ZP into Fy by gamma m naught, it must be less than or equals to 1.2 ZE into Fy by gamma m naught if it is a simply supported beam. Okay, if the given beam is a simply supported beam, then the value of MD must be less than this value. If it is a cantilever beam, the value of MD must be less than or equals to 1.5 times of ZE into Fy by gamma m naught. Now, what is here ZE? ZE is called as elastic section modulus. So you can refer the ZE values from the annexure H of IS 800-2007. And here ZP is the plastic section modulus, which you have found out for the section. All right. In the first step, I have said, so not in the first step, in the second step, we are going to find out the ZPZ value. That is the formula is M into gamma m naught by Fy. That is ZPZ equals to M into gamma m naught by Fy. This is what we have seen. So from this equation, you are going to get the ZPZ value. And from the value of ZPZ, you are going to select a section, select an I section, right? So whatever the ZPZ value of the selected section, that value you have to make it here. So that is called as ZP, which is plastic section modulus. Anyways, so these are the two conditions to find out the values of MD, that is the design bending strength for the simply supported beam as well as for the cantilever beam, right? So here the value of beta B is taken as 1 for plastic and compact sections. Okay, so the value of beta B is taken as 1.1 for plastic and compact sections, and the value of beta B, right, in the section classification, I said you have the plastic section, compact section, and the semi-compact section, right? These are the three sections. If it is a plastic and the compact sections, directly you can take the beta B value as 1. Okay. If it is a semi-compact section, the beta B value has to be calculated based on elastic section modulus with the ratio of plastic section modulus. Okay, and remember again, the elastic section modulus is obtained from the annexure H of IS 800/2007. However, we'll check while solving the problem. But most of the times, all the beams will be falling under either plastic category or the compact category. It is not the compact category also. Most of the times, the beams will fall under the plastic category only. However, if you experience the semi-compact section, we'll try to solve for the beta B value as well. So this is how you're going to find out for the low shear case. And now let's look at the high shear case. So if it is a high shear case, what is high shear case? It is V is greater than 0.6 VD. Remember this condition, V is greater than 0.6 VD represents the high shear case. So if it is a high shear case, the design procedure gets little different. So here you can get these values from clause 8.2.1.3 of IS 800/2007. So the formulas goes in this way. So for high shear case, please check down this image. For high shear case, okay, you have two conditions. MdV must be greater than or equals to M for plastic and compact sections, and MD must be greater than or equals to M for semi-compact sections. Remember, based on the type of the section or based on the class of section, the high shear case calculation will get different. Okay, now let's look at this one. So here MdV is nothing but a design bending strength. So for plastic and compact sections, and MD is nothing but design bending strength of semi-compact section. Now, how do you calculate these values? That is the value of MD. Remember, the MD value is calculated by using this formula, that is ZE into Fi by gamma M naught. Okay, so if it is for a semi-compact section, remember, if it is a semi-compact section, you have to prove the condition as MD is greater than or equals to M. Okay, this is what the semi-compact section says. So how do you calculate the MD values? You have the formula, that is ZE into Fi by gamma M naught. Now, what is this M? It is the factored bending moment which is calculated in the first step. Okay, we have calculated the factored bending moment and factored shear force in the first step. So that is the condition. Now, if it is a plastic or compact section, so it must be greater than MdV must be greater than or equals to capital M. This is for compact and plastic sections. Now, how do you calculate MdV? It is calculated by using this formula. Okay, MdV equals to MD minus beta into MD minus MFD. So here again, you have the values of MD and MFD. You don't know these values, right? So now how do you calculate? So before that one, let's look at how do you find out the value of beta. So beta is calculated by using this formula, that is 2 times of V into V divided by VD minus 1 whole square. So here V is the factored shear force and VD is the design shear capacity, which we have calculated, right? So here the next factor is MFD. MFD is calculated by using this formula, that is Z into FT by Z into FT, ZFT into Fi by gamma M naught. And again, ZFT value is calculated by using this formula, that is ZP minus AW into YW. Okay, so here YW is calculated by using this one, that is total height of the section divided by 4. And AW is nothing but area of the web, which is height into thickness of the web. So from this, you're going to get the values of the high shear case conditions. Okay, so it depends on the high shear case calculation depends on two categories. One is for plastic or compact section, you have the separate procedure, and for semi-compact section, you have the separate procedure. If it is a semi-compact section, you have to solve for this one, that is MD and MdV, MD condition, just this one, MD condition, and you have to prove that MD is greater than or equals to M. And if it is a plastic or compact section, you have to solve for this process. That is, you have to prove that MdV is greater than or equals to M. In order to prove MdV value, or in order to calculate the MdV value, you have this entire design process. Okay, so this is the next step. So for high shear case. So based on the high shear case or the low shear case, you have to adopt that particular process. Okay, make sure of noting down these clauses. So for high shear case, you have for clause 8.2.1.3, and for low shear case, you have the clause 8.2.1.2. Okay. Anyways, so the next step goes with the check for deflection. Okay. So in check for deflection, you have to calculate the maximum deflection of the beam, that is delta max. So the value of delta max depends on the loading conditions as well as the end supports of the beams, right? You have the different values of the delta max. That is 5 by 384 WL power 4 by 8 EI. You have the different values of the maximum deflection. So I'll talk about this maximum deflection conditions when that particular problem is being solved. Okay, but for time being, let's just remember the maximum deflection value for a simply supported beam carrying UDL load. Okay, this is the most common type of model which is given. So the maximum deflection value for a simply supported beam carrying UDL is 5 by 384 into WL power 4 by EI. Okay, where W is the weight of the member and L is the length, E is the Young's modulus, and I is the moment of inertia. So here I is nothing but IZZ. Anyways, let's just keep it as I only. I'll talk about that IZZ or IYY while solving the problem. So, and here the delta max value, whatever the delta max value which you have calculated, this value should be less than L by 300. It is not 1 by 300, it is L by 300, where L is the span of the beam. Okay, so if you prove this condition, then you can say the check for deflection is safe. Okay, if it is greater than, that is, if delta max is greater than L by 300, then you have to adopt, you have to redesign the entire section. Okay, that goes in a different way. I'll talk about that while solving the problem. Okay, anyways, so this is the entire design procedure of the design of laterally supported beams. But along with these 7 steps, you also have two more different steps. One is check for web buckling. So this is another step. Check for web buckling, and the second and the another step you can consider this as 8th step, and the 9th step is check for web crippling. Sorry, this is web crippling. Okay, fine. Here I'll write web buckling. So you have these 2 extra additional steps also, but these 2 additional steps, that is check for web crippling and check for web buckling, they need not be done for all the models of problems, but I'll let you know in which type of problem you're going to solve the check for web buckling and check for web crippling. So it is also okay to not to go for the design, to not to check for web crippling and web buckling, but it gives a better check if you do for web crippling and web buckling as well. Okay, so anyways, this is the entire design procedure. That is the 7 steps or the entire design procedures of design of laterally supported beams.